I'm delighted to introduce to you Professor Jean-François Allemand, who joins us from Paris. He's an experimentalist in the laboratory.
Is it a problem?
Not at all, it's fantastic. From the Laboratory for Statistical Physics in the École, Normale, Supérieure. And you'll be telling us a bit about some of the work you're doing. Thank you very much for traveling to South Africa.
So far compared to others. So. Yes, so I work in the École Normale in Paris, so maybe a comment, an idea that might look strange to call a school École at the same time Normale and Supérieure. This is simply because École Normale means a school where you train people to become teachers later, okay, and Supérieure is here because you prepare them to become teachers at a highest level. This is the reason of this normal and superior. So my lectures would be about lights around DNA, particularly the aspect related to the mechanics. So it means that I will need some biology at some point. So I don't know your expertise in this field, how far is your last biology lecture. So if you have any question, do not hesitate. So I will start with a brief reminder. So, what is DNA for you? Please.
What is DNA?
Yeah.
Well, it's the code that determines the expression of all the cells in our body.
It's a starting point, yeah. So, the code is written with how many letters?
4.
Simply 4, yeah. A, T, G, and C. And so you simply have to see where I should press. It's here. Okay. So between two AT bases that are corresponding, you have 2 hydrogen bonds. Whereas between G and C, so adenine, thymine, guanine, cytosine, you have 3 hydrogen bonds. So you have a double helix structure, as represented here. So between 2 bases, you have a distance of 3.4 angstroms. I don't know if the resolution is good enough. I think you were right, you have something like 2 images that are close to each other. And what will be important is that this polymer is also an helix that has helical bridge. It is about 3 nanometers. That corresponds to about 10.5 bases per turn. Okay, so this you have a long genetic code. I'm just thinking about what you said. It's not, you have regions in the genome that do not code for something. So this is why you cannot simply say that it's where you express the gene. This is the remark of that way. So so this molecule is, and this is the reason maybe what I'm here can be quite long, because it's a long polymer, and this polymer can be so in our cells we have 3 bases in our body. So if you consider that you have 3 billion bases that are separated by a distance of 3 angstroms, it means that in each of your cells you have something like 1 meter of DNA. That means 1 meter of a polymer. Does someone has any idea about this? Well, there was some biology remarks this morning, so I assume that someone can reply. What's the size of a cell, typical human cell?
A few microns. Like a few microns.
Few microns. Who is doing better? More or less?
10 microns? 10 microns?
10 microns? So, who made a remark about the cytoskeleton this morning? And so?
I think it's about the 100 micron.
It's on the order of 100 microns, yeah. This is physical size of a cell. And if you think about your body, what is true is that in your body you have a nucleus, and the nucleus will be about a few microns. 5 to 10 microns, this is the order of magnitude. So in each of your cells, you have to put typically 1 meter of a macromolecule and to place it into only a few micron compartments. And then you start to see that you have a physical problem that you have to solve in order to do that. And if you think about biology, you know that cells do divide. And so not only you have to pack a long piece of DNA into a small compartment, but you also have to duplicate it and at some point do a separation between the two daughter cells. And so this is where you face some problems and where the physics of polymers is quite important. So just to go back to what you said, the general idea is that shows the DNA here, that is a support of the heredity of the genetic code. You have some enzymes that recognize the DNA that duplicate it. So those enzymes, DNA polymerase. So this is to duplicate. So it's an enzyme that, I'm going back to this point later during the week, but that goes along the DNA molecule and use the chemical energy to move. So you have to think, as a physicist, you have to think about this as a motor. So you have to duplicate the DNA, you have to make proteins in the end. So to do that you have polymerase that copies the DNA to make RNA, so which is another macromolecule. So this is done by the enzyme called the RNA polymerase. So you go from DNA to RNA. And then you have other biological systems that goes from the RNA to synthesize proteins. And you also find in nature enzymes that goes from the RNA and go back to form some DNA, like all the reverse transcriptase. Okay, so this is the basic knowledge that we need to keep in mind, because the polymers that we are going to work with is related to some biological functions. Right. So why is DNA a good polymer? What's the interest of working with DNA compared to other polymers?
You can program it to link up to specific other, or like pieces of DNA can match exactly to other pieces of DNA based on the local code, right?
Exactly. So the good point is that you can use what nature has done. And what nature has done is all the enzymes. And so if I think about, you're talking about, among the enzymes, you have some restriction enzymes. Those are enzymes that cut DNA at specific sites. So in your life, you can find those enzymes, typically in bacteria, that are used to cut to protect the DNA from foreign DNA that would come from viruses that would attack the bacteria, for example. So I can give an example. So there are many of them. So there is one that I think, which is, I mean, you have different names. So the name usually tells you from the organism which it comes from. So this enzyme, the specific one, recognizes on the genome the specific sequence. So it means that I will have here a G, here A, a G, a C, a T. It should be a G here, so it's going to be a C here. So this enzyme recognizes the DNA and it will cut the DNA at some specific sites. And as it was mentioned, it means that here you are going to generate DNA extremities that will have bases when these two pieces will be separated and the DNA will be cut. That will generate two pieces of DNA, while you will have here bases that will not have complementary bases in front, and so they are going to be able to bind to some complementary sequence. So I'm not here. I need another color. So if I use this enzyme, I'm going to prepare DNA pieces that will have extremities, that will have some, I will have A, G, C, and T. Okay, so here I will be able to make 2 hydrogen bonds, here 3, 3, and 2. So any piece of DNA that would be in fact similar to this one can be recognized and be linked to this piece of DNA. This is one point. It means that I can cut a piece of DNA, mix it with something else that will have some special properties that will bind, and then I will be able to manipulate the DNA that I have because I will be able to bind some specific ends to the polymer I want to work with. Okay? So you can do this on one side. You can do something different on the other side. And so by this means, you can take a piece of DNA, bind something on one hand and something on the other hand. And this is what we are going to use for when we are going to pull on this polymer. Okay? This will be one of the purposes that we are going to have. Another point is that, as you know, you have almost the same DNA in your cells since you were conceived, when you were at the single cell level. So it means that in nature you have many enzymes that are able to make many copies of the same DNA. When I mean same, it is exactly the same. The extension is the same and the genetic code is the same. There are some errors, but there are some systems in your life that allows to correct the errors that you can make when you are making copies. So on average, you make an error every billion bases, which means that you have exactly the same DNA in many copies. Okay? And so this is interesting. So you can, and the other point is that you can have long polymers. Since we said that it can be a few microns, few millimeters. So you can have something that is long, that have exactly the same length, and that you can manipulate. So here you can put things on extremities, but you can also use some fluorescence to label the DNA. And then to visualize the DNA. So like this, you are going to be able to grab the DNA by the 2 extremities, and you are also able to watch it if you need. So some people, for example, the group of Steve Chu, it was something like 15 years ago, that he studied the behavior of DNA molecules inside the flow, and so you can see what is the shape adopted by the polymer in the flow, for example, if you label it with fluorescence. And I'm going to show you some movies where it was done more recently to study the mechanics. Okay, so this is one of the aspects that make the DNA is a good model. So I didn't use the clicker, but I'm going to ask you the same question. What is going to happen when you hit a polymer? Okay? So do you think it contracts? Extends? Nothing? You are going to have the full explanation now. So the general idea is that this morning the experiment, the idea was to take a material that was made from polymer and to see that it was contracting when you were hitting. Now the experiment that I have in mind, so I will describe the experimental technique later, is that you have polymer that will be attached to some micron-size object, and we are going to be able to apply a force or through optical tweezers or through a magnetic field on this bead, and this bead is going to extend the polymer, and so we are going to get the elasticity of a single polymer chain. Okay, this is what we want to measure, and we want to interpret the result. And so we start by making some modeling. So the simplest model I was proposed this morning is that the polymer is a random model. In the simplest model, you don't care about the chemistry. It means that you know in chemistry that you have some specific balance between two chemical links. For us, it will not be a problem. In fact, if you do the calculation, this is simply a restating of the problem, so it's not. So in our model, we are going to have a random walk, and the polymer, one segment compared to the other, can take any angle. Here we have an angle theta, and theta belongs to 0 to 5, without any difference. And so it can rotate in this direction also. And we do not care about the chemistry, which means that we don't care either about the steric inverse. So it means that the polymer can come back to the same position. So this is the simplest model. And its name is pretty jointly chain model, or FGC. So we have segments that can take any orientation, and so it's a random mode. So I just want to make some recall about what's happening in one dimension. So it's a random mode with step size that we take fixed here because it's linked to the chemistry. We have a polymer that has the number n monomers. So we are having a random mode with n plus steps that are going into the positive direction and n minus that are going into the negative direction. So the position that you get after n steps is simply the difference between n plus and n minus times the step size. And so if you calculate the probability to be at the position x after n steps, it's given by the combinatorial C n plus n, that is equal to n plus n minus n. So I think that you did that already in former classes. So you know that if you take the limit when n is large and you know that you're not going to be very far from the position that you expect that is at 0 because you don't have any asymmetry here, you get the result that the probability is a Gaussian that is centered on 0 because you don't have any preferential direction, and with a width that is given by the n(a) square. And this is valid so when n is large. So as a consequence, you have a typical distance, the radius of gyration, this is why it's written Rg, that goes like the square root of n. And so the only typical distance here is a, the step size, and so it counts as n to the power 1/2. So this is what you get when you do random walk in one dimension. So this is what you can find quite easily in standard books. This is in one dimension. You get almost the same thing if you replace a squared by a squared divided by 3, because you have 1/3 relation a squared square that is equal to a squared if you are in 3 dimensions, and so as all the directions are equal, this is why you have this factor of 1/3 here. And something that is important, that in the polymer fields is important, that you don't have the problem of excluded volume here because we didn't take into account steric hindrance here. And so the scaling behavior that you get here, n to the power of 1/2, has to be modified when you have this excluded volume effect and when you have some swelling. Here, for the experiment that I'm going to present, it's not critical because the DNA that we have, that's a calculation that I should do. What you can get easily are DNA molecules that are few microns long. Does someone has any idea about, I'm going to come back to this point, any idea about the value that we could take for A for the DNA? Who work with polymers here? I'm sorry, so this is, what numbers would you have in mind for a standard classical polymer? This is the distance of the random walk. For a standard one or for the DNA?
For a monomer. Sorry.
With the size of, you would expect it to correspond to how many chemical bonds, for example? I have no idea. Do you have any idea? No? So we are going to that point later, but from the experiment that I'm going to describe, you have A that is about, let's take a number, I should take something with a factor of 2 that will be something like 50 nanometers. Sorry. So it means that if I take a DNA that is 5 microns, so 5,000 nanometers, I divide by 50, this is number of steps, I get something like just 100. So typically we have 100 steps in the experiment, so you can be 5 times, 10 times more, but it's a typical number.
Sure, what's RG?
RG, you see, the number here is exactly what you have here. So it means that this number is the typical size of the distribution. Did you see any simulation of a random walk on the computer? I think we have some homework for tonight.
I can give them that code too. You want 1D, 2D, and you want self-avoiding?
For tomorrow, I think 1D will be enough. No.
1D, okay.
And RG is for radius of gyration.
Yeah, it's a radius of gyration. This is
Like mean square, well, the square root of mean square displacement. Mean square displacement is linear n.
This number is exactly the width of the distribution here. So what you have, if you look at the probability, this is, it's centered in 0. This is x, and this is the probability to be at the position x after n steps. Okay? It's a Gaussian, and the width of the distribution goes like n to the power 1/2 times a. Okay? So it means that it corresponds also to the typical size of the polymer chain when you look at it. Okay? If you were able to see the polymer, so by using some fluorescence as I mentioned previously, you would see a bright spot whose size would correspond to this number. Okay? Corresponds to typical size of the polymer. Okay? Or you may think about also, because it's the same problem, you may think about the diffusion. This is the typical distance that you travel after making n steps after a random walk. Okay? So on average, you get something 0. The Gaussian is centered in 0, but you have some fluctuations around that, and typical size of fluctuation are a bit like this. Okay? This is typical size of your polymer when you look at it. So when you make a simulation like this, so it means that you are going to make 1 step, 2 steps, and so on. You are going in every direction after each step. Okay? If you don't have a high density at the center, you won't be, you won't have any problem of going back to the same position. Okay? So here, in typical experiment, you only have 100 steps. Okay? Which means that we don't have many ways of getting back to the same position. So we don't care that much about the steering engines. We don't care that much about the fact that we were already at a position, because it's very unlikely that we go to the same position. So this effect is not important in the experiments that you can do on such system. We will see only an example at the end of this lecture, or maybe the next one. Okay?
That seems to kind of set a random walk.
Taking this into account would be a self-harmonic group, yeah. So this is the exercise for, not for today, but for the day after. Okay, so it's not important because experimentally, I mean, it is important in the physics of polymers, okay, but it's not critical in the experiments that I'm going to describe because the density of the random walk is not high enough. The molecule, or if you want, in other words, the size of the molecules that we have, n is not large enough so that we can fill it. It's okay? You can go a step further. So, the goal that we have is to understand this in the end. So, we want to see what's happening when you have small perturbation around the system. As it was mentioned this morning by Mark, you have this relation for thermodynamics. And what is interesting in soft matter is that this term can be important. And in the model that we have, there is no energy associated to the binding of the chemical bonds. Okay? We didn't take that into account. It means that the internal energy, U, is simply equal to 0. And the only term that we have comes from the entropy. And the entropy we can calculate it because it's simply the Boltzmann relation, telling you that it's the Boltzmann constant times the number of configurations that you have. And we have seen previously that we have something that is Gaussian. And so here is the probability. So to get the number of configurations, you simply have to forget this term here. And so in the end, if you do the calculation, you get to this result, meaning that the entropy depends on the position. So the entropy means number of configuration when the one extremity is bound at position 0, 0, 0, and the other extremity is at position x, y, and z. And so you have previous calculation that gives you this number. So if you go far, you will have the entropies that will decrease. And you have this distance that comes here, that is the radius of gyration that you find again here. So you have the number of configurations from the previous calculation. So you are able to calculate the entropy. So you are able to calculate the free energy. And so the free energy is simply temperature times the entropy, and then you have this relation. Now you want to know what's happening when you stretch slightly your polymer. It means that you want to know how varies the free energy when you change the typical distance that you have. So you have to take the derivative, and this corresponds to the opposite of the force on the system. So you take the derivative of that. So here you have the R square, you have to divide by derive by relative to R. So you get a factor of 2 that comes, maybe I should write it. So the free energy, I can write it, 3/2 of kBT times R squared divided by A2. So I derive this relative to R and I get this result. And so you see then that the force that you apply to stretch is proportional to kBT times the distance divided by a factor that is typically the width of your distribution. And so you see that you have a force that is proportional to the distance, the extension distance. Okay, so this is the relation of a spring. There's a force that is proportional to displacement. And the key point here, so I remind you, F is equal to the stiffness times the distance. The point here is that the stiffness is proportional to the temperature, kBT divided by Na squared. So it means that your polymer behaves like a spring whose stiffness depends on the temperature. And if you increase the stiffness, if you increase the temperature, you are going to increase the stiffness. And so at constant force, if you have a spring that is more rigid, you are going to contract. Okay? This is a basic idea that allows you to understand why when you hit a polymer, you have some contraction. And you see that it depends also on the number of monomers, and it also depends on the typical step size. Okay? If you take, so we said that for DNA, the typical step size is 50 nanometers. If you take A for a standard polymer, I have the one for the polymer. It's typically 2 to 3 chemical bonds, so it's going to be few angstroms. Okay, if you take a standard polymer. So it means that if you take a chemical polymer that will have a step size that will be functional, it will be A will be smaller, so K will be larger, so it will be more difficult to extend. So the smaller the step size, the more difficult it is to extend the molecule. And we are going to see that this is counterintuitive. Okay, so this is what's happening when you have the polymer that you have some perturbation around the mean position. But in the experiments now you can have the full curve, meaning that what we want is to get the full relation. So this is valid when R is close to 0. Okay? And we want to see what is the general relation between R and the force. So you had the physical interpretation this morning. You have many configurations that correspond to a non-extended polymer, and when you are going to stretch it, you are going to reduce the number of configurations. And when you exert a mechanical force to extend the polymer, to fight against the entropy. Okay? You are not fighting against any enthalpy, any pure energy. Here the mechanics fights because you reduce the number of configurations. This is why usually the term entropy. You have to exert mechanical force to reduce the number of configurations that your polymer can adopt. And for me, this is the most intuitive way of understanding what is entropy. Because the force is something that you feel quite easily, okay? Whereas entropy usually is quite a magic function. Okay? And here you can relate the magic function to the mechanical sensation that you can have every day. So as I said, the relation that we have here is valid only close to a non-extended polymer, and so we want to have general relation. What is the relation between the force and what is the notation that I took? So the force and the extension. That should be valid for any extension, whereas here for L goes to 0. So, in the freely jointed shape model, all the segments are independent. So what you have is that you have monomers where you don't have any force, and the force is equal to 0. Any monomer want to take every direction possible. So when you don't have the force, your monomers want to go in any direction. And because of thermal fluctuation, they do explore other configurations. Okay? When the force is different from 0, then what you do is that you orient the monomer in the direction of the force. So you have an external field here, the force, that tends to align some segments. Okay? That this reminds you something. I can change the field. I can say that I'm having a magnetic field that is going to orient some magnetic dipoles. Okay? Or for those who are chemists, it's more likely to have an electric field that is going to orient electric dipoles. Okay? So this is magnetic dipole oriented in a magnetic field. This is what's the name? No? Am I wrong? You have dipoles that are free to move, the gas dipoles. You put a magnetic field, they are going to orient in the direction of the magnetic field. This is exactly the same problem. Okay? This is due to the work of Allemand. Okay? So, in this case, what is the energy? So, energy of a magnetic dipole mu in magnetic field B. The energy is given by very simply a sign that comes here, which makes that the energy is minimum when the angle between the two is equal to 0. Okay? So here, the energy when you have a force is something like that. Okay? The energy when you like that, the force on materials that to extend by a length dl. Okay? So here we're not going to extend every segment, but we are going to orient. So we have something like that, and we will have a force that will be put in this direction and a force that will be put in that direction. And this is going to orient the system, and the energy will be minimum when the angle here will be equal to 0, and we have the same energy. So the energy here, that will be minus F A plus theta. Okay? So we can do the same calculation that we can do when you study the Langevin paramagnetism. And we simply use the Boltzmann's law. We have the probability of having the system with a given energy, so here the energy will be equal to 0, with a given extension that is proportional to the exponential of minus beta, beta being 1 over kBt, the standard notation, times F times L. And so as all the segments are independent, you can write the partition function as the product of the partition function of every segment, and then you get to this partition function that you have to calculate. But the most important, because you may have done already the calculation for the calculus for the Langevin paramagnetism, you get exactly the same result, and the result is the Langevin function. So we have, this is going to be the distance between the two extremities. On the polymer. And this is going to be It has to scale as the total size of the polymer, total extension, times over the hyperbolic tangent of, I didn't put the parameter, FA divided by KBT minus 1 over FA divided by KBT. And you have the same result if you change FA by UV when you study the parameter. So, does this correspond to what we want? What's happening when the force is large? We have to find this, to define this a bit better. What's happening to the hyperbolic tangent where when the argument is very large, it goes to 1. This 1 divided by something that is large goes to 0, so it means that the extension goes like
Excuse me, can you turn the lights on? I'm having trouble seeing. Is there those lights up there? Do those go on? Thank you. That helps a lot.
So when the force is large, what you find with this result is that the extension goes like the full extension of the polymer if you were following it. And so you have a fully extended polymer. And this is what you expect. So can we define a little bit what means F being large? Is large compared to what force? I simply said that it's large compared to 1, which is not in fact a good value. What is the typical force that appears in this relation? From dimensional analysis, you have a length, so this has no dimension, and here you have the argument of a tangent that must have no argument, so it means that this you could write FA divided by KBT, no dimension, so it can be written F divided by FC, with FC being equal to KBT divided by K. So this is not a good way, but I should have written here is F large compared to FC. Okay. What is going to happen when F is small compared to FC? Does someone have in mind how this looks like? Usually people don't. So this is the Normale function, and this goes to x divided by 3 when x goes to 0. So it means that in this condition, it is NA times FA divided by 3 KBT. So if I do that, I get the force that is equal to the extension by factor of 3, NA squared, and I have the 3 KBT here. And as I don't manage my blackboard so well, I erase the relation that we had previously that was exactly the same. Okay? So we have, once again, the force that is proportional to a displacement, so we have a spring, and we find, again, the same value for the stiffness of the spring that depends on the temperature. Okay? So we find the same relation in the regime where the force is small compared to FC. So here I've been taken an approach where I'm changing the force, but you may also have the same discussions. Large F is equivalent to low temperature, or small f is equivalent to high temperature. So this relation, if you take the low temperature limit, so if you cool down your system, what you are going to have is you will have your polymer adopt this configuration. And it's because you heat, because it's an entropic system, that when you heat, the fluctuations are important, and then you reduce the typical size of your polymer, and you go to zero at very high temperature. Okay? So the problem of the polymer is exactly the same, at least in the free Jean chain model, is exactly the same as the one that you have in magnetism. And so you can use all the calculations that you did when you were younger to get the results. And if you want to use this, you may have forgotten. Okay, and now we have a full relation between the extension that we have between the extremities and what we expect with this model. So experimentally, the curve represented by the free Jean chain is green one here, and the experimental points that you can get are the red ones here. So it means that you see, so this is a logarithm of the force, okay, and this is a relative extension. So this corresponds in this model to L divided by NK. So you see that it's not that far, but nevertheless, it's possible to make a better model, and this is what we are going to do now. But you have here first the simplest explanation corresponding to what Mark presented this morning, and you have the critical point that is the force here to extend the polymer is here to fight against the entropy, to reduce the number of configurations. And this is a critical element of this model that we are going to modify later. So the model that you have to take into account to describe more precisely the DNA is called the world light chain model. So instead of having the polymer that is random walk with steps that are not correlated, now you consider the DNA as a beam, and you will have some cost to bend it. Okay, so if you want to have an angle along the position, so it will be continuous curve but not discrete steps. This is the key element, and so it will cost some energy to bend it. This is a critical point here. So on such a system, as it costs energy to bend it, it means that it should be a straight line. So you should get something like that. The point is that you have thermal fluctuations that make that at every position you receive some shocks, and the shocks make you deviate from a straight line, and so after some distance you are going to lose the correlation in orientation that you have. And this distance is called the persistent length. Orientation. So if you hold your polymer at the initial monomer, after some distance, you will lose the orientation that you have given initially to your polymer. So this could be enough. So if you keep that in mind, it will be good enough. But if you want to define this a bit more precisely, you have to do a little bit more of math. So here, I forgot to make the drawing. Here we consider our polymer, and we will have 3 different points, A, C, and B, that will be at the origin of our and Z here. And so there is a tangent vector here, TA. You have the, okay, I'll take it here. You will have a tangent vector at the position C, and you have a tangent vector at the position B. And so we take the distance between A and C that is large compared to the crack center. The distance over which I use the correlation in rotation, and I'm going to, let's think, I call it phi. Okay. And we want to see how the cosine of the angle that takes the polymer along the chain varies with the distance along the chain. So this is the curvilinear. So the cosine that we are looking at is given here. How the orientation is done, so what is the average projection of the tangent vector C on the tangent vector A. Okay? So in the way I define my function here, it's simply given by the cosine of the angle theta given after a distance SA plus SC along the chain here. But you may decompose the two vectors A and C on the tangent vector B, and then you have the different terms here. So here you have the projection along Z of the vector TA, here the projection along Z of the vector TC, here you have the projection on X, here you have the projection on Y, and so this is what you get if you take all the components of A and C in this referential. So we need to get the average value of the system, and as we have some no specific orientation around the axis, around the direction of TV, as we take points that are quite far away, we don't have any correlation between the orientation, and so the results that we get is that the average of all these terms, those ones are going to zero because we don't have any preferential orientation in this direction. Phi is going to get the angle in this direction. Then the only term that will remain is the cosine of SA times cosine of SC. So basically you keep only the first term because you don't have any specific orientation. So it means that this product, or this function, the cosine of theta after a distance, so I took SA but I could take U and B, is equal to cosine theta U times cosine theta U. So I have a function whose value of a sum is a product on the two values here. So here I took 2 points that are at a distance that is quite large, but if I take the limit where U when U goes to 0, so this is the value of cosine theta S when S goes to 0. Basically, we are taking the point C and we are bringing it very close to A. Then if I get very close, the orientation should be the same. So I should get to 1. So we have a function, cosine of theta is a function whose the cosine of the sum gives the product of the cosine, and the value goes to 0 when this goes to, the value goes to 1 when you go to 0. And so the result, you know a function that does this job, that is the exponential of the parameter. The product of the sum of two, the exponential of the sum is a product of the exponential, so we have this relation. And we also know that the exponential goes to 0 when it goes to 1, when the parameter goes to 0. So we may assume that the result will behave like this. So we could define the distance length. So here we have the exponential of the parameter times the distance. So this parameter has a dimension of the inverse of the distance. So we may say that this parameter is the inverse of the distance, and we may define this as a distance over which we lose the orientation. We could define the distance length in this way. But I think that there is another approach that brings some interesting elements. You may use this definition of the distance length. So this comes from the, when you bend a beam of any material for at least small deformation, you have a deformation that depends on the radius of curvature of your material. Okay? So you will have the energy cost to bend the material that is proportional to the integral of the inverse of the radius of curvature. Okay? And so you define the distance length psi simply as the energy it takes to form a circle. If you make a circle of radius psi, you get a value of kVt. So you can use this as a definition. So your polymer is going to bend. Okay, you will have local curvature along your chain, and you are going to sum all this contribution to get the energy. And so the parameter here will be the distance length. So the local curvature is defined. You have a curve, you have theta, and if theta varies, okay, then you have some curvature. So it's related here. If your tangent vector has an orientation that changes when you move along the polymer, then you have the curvature that is present. So for those who are used to mechanics, if you take some classical textbooks, the parameters that you have here, that is here to define the distance length, is written as kVt times time. In notebooks, you find that it's something that the Young modulus times a parameter that depends on the geometry of the material that you want to bend. So here it's a definition that comes from pure deformation mechanics. And so this is what we are going to use to go more precisely to define the distance length. So if I take now this model and I say, I take my polymer, I give an orientation theta equals 0 at some point, and here I will get theta 0. Okay, after a distance, I give a name here, I get L. Okay. So I'm simply taking, as an example, something where I take L that is smaller to the distance length. So the radius of curvature, the square of the radius, the inverse of the square of the radius of curvature is given by this relation. And so you have to minimize this energy, so you use Euler-Lagrange, so you remember that? Euler-Lagrange, okay. So if you take the minimization, it tells you that in this case the second derivative of theta compared to s is equal to 0, which means that theta varies linearly with the axis. So with something that, if I took something where theta is equal to 0 for s equals 0 and theta is equal to theta 0 with s equal L, then you get this relation for theta. This is the equation that follows theta along the chain. And this allows you, when you replace this relation here, to get the energy. And you get an energy that is proportional to theta 0 squared. So you have an energy that is proportional to the square of a parameter. You are at equilibrium, so you can use the equipartition of the energy. And the equipartition of the energy tells you that the average value over the fluctuation is equal to 1/2 of kBt per degree of freedom. So here, our polymer can move in this direction and in this direction. So here we have 2 degrees of freedom. So the average value here will simply equal to twice times 1/2 of kBt, and so it's going to be kBt. So we had a relation for the curve theta that we can use now. When this is going to be, when s is going to be small, this is the case that right here, it's going to be theta squared divided by 2. So if you use this relation that we got from the previous results with alpha, that you use the relation that we have here, you come to this relation, and from that you deduce that the alpha is equal to the inverse of the percent length, so it means that the theta s is proportional to the exponential of minus s divided by the persistence length. So the persistence length is what I said initially, but here it comes with more relation with mechanics of the polymer, the sentence. The distance to the correlation in my equation. So I feel that you are tight, but there is one point. Why did I make this element? This calculation is that here you see that it will cost some energy to bend your polymer. Okay? And so it means that the distance over which you lose the correlation of orientation is related to the Young modulus of your material. The stiffer the material, the more difficult it will be to bend it. Okay? And so the longer will be the persistence length. And so there is a relation between how difficult it is to bend the material and how flexible will be the polymer. But where it is counterintuitive, and I think my time is almost finished. I'm going directly to this relation, and maybe I will come back to next time. There is a relation, there is simply a factor of 2 between the step size in the random walk model and the persistence length. Okay? And so the more rigid is the material, so the longer is the step size of the monomer ball. So the more rigid is the polymer locally, then A is large. If it's more rigid at the local, then it becomes easier to stretch the polymer. If the polymer is made from material that is rigid, then it's easy to extend because A is large, and so the proportionality between F and L is small. Okay? And so this is why it's counterintuitive. It's easy to stretch a material that is very flexible locally, and it's difficult to stretch. I did it in the wrong way. Okay. I did it in the wrong way. Something very flexible locally is difficult to extend. Okay, and this is really not intuitive. And this is once again due to the entropy origin of this elasticity. Okay? So there were some calculations, so you can go back to calculations that you did already from the paramagnetism. But keep this in mind, related to what Mark mentioned this morning, that the origin of the entropy of a polymer, of the elasticity of a polymer, comes from the entropy from the fact that you reduce the number of configurations. And so temperature is important, and this is why you have this counterintuitive fact that when you heat a polymer, it contracts and shrinks. Okay? And the next time I'm going to show you how you can measure these functions on DNA. Okay? So I see that you are tight, and I wanted to go a bit fast at the end. Sorry about that.
The concepts that Jean-François has introduced are going to be used in a few different contexts throughout the coming 2 weeks. So you'll probably be hearing some of these things again. But just think about what you've heard of today. You've heard of rod-like objects. And now we've actually discussed the continuum of when you get from a rod-like to something that's persistent in some other way, to something that's completely crumplable in another way. And we've got the length scales and the persistence lengths and things like that with which to describe when we're referring to which situation in these molecules. But I think that we have to rush on. I hope there are 1 or 2 questions at least. Yes.
So there was this function, it was curly L of x.
Yeah.
It was something like 1 over tangent x and 1 infinite function. What makes that function better to describe flexible polymers? What's special about that function, I guess, that gives you almost perfect agreement with data?
The Langevin is not the one where the fit is the best. Langevin is a green one. So you see you have some discriminative. So this is why people made some refinement to get the blue one, okay, where you have the continuous curve, but it's the less intuitive elements are already in this function. Okay.
And we didn't finish going with the worm-like chain model?
The worm-like chain, the problem is that, well, you have the main elements that you introduce. So now, with what I've given here, you have the energy, okay? And so you can use that to calculate a partition function, okay? But then the math becomes more tricky, okay? And so you don't have an analytical solution, but I will give you some tricks so that an experimentalist can use, okay? So it's more difficult than to compute the full curve here. And in fact, it was solved only in 1994 by Jean-Marco and Eric Sitjar. Okay? But to understand the elasticity of the polymer and corresponding to the experiments that Mark have shown this morning, it's, the other one, the Langevin, is the simplest one. And the good point is that it goes from the polymer physics to paramagnetism, so it goes through different fields of physics. But it's good to know this element. So the idea is that you have, as you have independent segments, they can take any orientation they want, okay? And when you add the force, you tend to orient and you favor the orientation that are in the direction of the force. This is the key element. You can forget on most of this.
Questions at this point? Yes.
So, as for DNA, I can imagine a lot of contributions coming from the electrostatic repulsions. So, like, how does this theory actually affect it?
For DNA, in fact, of course, it's a charged polymer, so DNA is negatively charged because you have some phosphate groups on the side. But it's not that critical because you have some, there is, and you will have some steric repulsion also. But it's not so critical because you have the screening of the charges that is the condition where DNA is working at. That the valence, it's a notion that you know, or you have some screening after a distance that is much smaller than what you have for the presence length. Okay? So DNA is rigid on distances that are large compared to the valence. Okay? This is true for double-stranded DNA, but it's going to be very different when we are going to move to other polymer. If you take a single-strand polymer, DNA, meaning that you can denature the DNA, then you will have this contribution that will be larger. Okay? There is some contribution, but it's not as important as you may expect. Okay? But it is, but it's not so crazy.
Okay, thank you. Then I think I'll hand over to Ivan, who's starting the final session.